Okay, good afternoon, everyone. Uh, let's see. If you haven't seen the announcement yet, I did post all the quiz solutions that are there they're available in the class notebook. Okay, there's a separate section under all the lecture slides that says quizzes. Let me bring it up. How many of you saw the announcement and how many of you have referred to the quizzes or saw the quiz solutions? So just a few. How many of you have never used the class notebook or not accessed the class notebook at all? All right, let's switch over here. So this is section 1, this is section 2. Pretty much they're both in sync. When you go to Content Library, you should see everything at your end. And both you have a section called quizzes, and the quizzes have all 4 solutions in there. So you can check your work against these. And the grading is ongoing, so you should have feedback on that also. Okay. The other thing I would like to note is that we are more, it might not seem like it, but we are more than halfway done with our course material. Okay. Not in terms of time, but actual course material, we are more than halfway done. And we are in week 5. Okay. So at times it might feel as if we are moving very slowly, but just letting you know that most of our course material, like 50% of it, it's done. Right. Most of the material so far was based on your prereq physics classes, but now we'll get into applications which you perhaps may not have seen before. So case in point today is how will we use a resistive circuit to create some other voltage or current quantities for a application. All right. So in today's discussion, we are going to look at a design example where we are trying to clamp an AC signal or an AC waveform with a particular DC value. Now, let me explain those terms. You're familiar with AC and DC. We spoke about this at the beginning of our course. DC is a constant value of either the voltage or the current with respect to time. AC is if the voltage or current changes its value with respect to time. More often than not, AC is represented as V of t and I of t. This is just a refresher. I think I pointed this out before. It simply indicates that the voltage is a function of time, current is a function of time, meaning if you enter different values of time, 0, 0.1, 0.2, 0.3 seconds, or any units, then the voltage could be a different value at any point in time. Okay, so that's V of t and I of t indicates that it's AC. So here we have an AC waveform. This AC waveform, this is a square wave which falls under the umbrella of a rectangular waveform. By the way, waveform, signal, they are kind of used synonymously. Okay, so they're kind of synonyms of each other when it comes to electrical engineering. So it's a rectangular waveform. And as you can see here, there is a positive cycle and there's a negative cycle. So typically, this is known as the on cycle. Actually, I would say, and this is known as the off cycle. And the ratio of the on and off cycle is known as the duty cycle. The time that it is on and the time that it is off. If this duty cycle is 50%, meaning they're both equal halves, then it is known as a square wave. That's it, okay? So rectangular can have any ratio of the duty cycle, but if it is 50%, then it's a square wave. The height or the amplitude does not matter. So far, so good. I believe you have already done an experiment with square waves, right? Okay. So on an oscilloscope, when you look at this, have you ever noticed that on the left side of the screen, there is a ground symbol? If you haven't, then the next time you're in the lab and you're using an oscilloscope, take a look. You will see this kind of symbol, either a triangle or you'll have 3 lines arranged in a triangle. It's very tiny. It's on the left side. What it is showing you, it is showing you the reference level for that waveform. Whether it's a sine wave or a square wave, doesn't matter what kind of waveform you're observing, it will show you the reference, okay? If that reference is at ground, okay, if that reference is at ground, then that waveform is centered exactly above and below that reference point, meaning it's running in the center. Half of the waveform is above the reference point, and the other half is below the reference point. So in this square wave that you're observing right here, it's exactly 5 volts above reference, and then it falls 5 volts below reference, +5 and -5. Okay. And so the average value of this waveform would be 0. Okay. Does that make sense to everyone? Right. Now, if you want to clamp this reference level, okay, not clamp. If you want to change the value of this reference level, either so from 0, you either go in the positive direction, or from 0, you go in the negative direction. Meaning you're taking that waveform and you're taking the middle point of that waveform and you're shifting it above 0 or you're shifting it below 0. That is known as clamping. Okay, that process is known as clamping. You're clamping the waveform at a particular DC level. So shifting the center of the waveform either positive or negative is known as clamping. Okay, clamping is an important application in circuits. There are oftentimes, not oftentimes, when we use amplifiers to enhance our signal, whether to increase the voltage or the current or power, it will have some DC component in it. So if you want to remove that DC component, meaning our waveform is shifted up in the positive direction, then we need to shift it back down, bring it back to 0, right? So we need a negative clamping circuit. Sometimes you also need positive clamping. So if a waveform is shifted below ground, then we need to bring it up. So in this example, that's exactly what you're going to do. We have a square waveform as our input. So this is V in of t. A voltage as a function of time that is applied to input, hence V in of t. And the output voltage is required to be shifted from 0 to +5. Okay, 0 to +5. So this waveform at input has +5 and -5. So the total swing in that voltage is 10 volts. So it is referred to as a 10 volts peak to peak value. 10 volts peak to peak value. And we are asked to shift it from 0 to 5. From -5 to 5, you're only asked to shift it to 0 to 5. And in the design problem is we use only a resistive network, meaning we are designing this solely with a resistive network. We can use a diode to do this too. Just a single diode can accomplish the task. But right now, we're only using a resistive network. All right, let's take a pause. Let me know if you have any questions. All good? Okay. All right. So we need a square wave that goes from 0 to +5. Okay. As I said, we could accomplish this using a diode. So one resistor, one diode, and we're done. Okay. We just get 0 to +5 volts. That was known as a half-wave rectifier. That's something you will learn in 315. Unless you did. No, we didn't do. Okay. So resistive network. So then we decide on what we want to do, right? So at this point, we're not changing V in of t. All we are changing is, effectively, we are simply removing the negative cycle, right? It's 0 to +5. So all we are doing is we are removing the negative cycle. So the difference between these two is that this is taken out. That's effectively what we're doing, okay? Anyway, so what we can do is we can take our waveform, since we're shifting it up, we're going to take our waveform and we're going to add a 5-volt DC value to it, okay? That would shift our entire waveform up. Anytime you have an AC signal and you add it to a DC component or a DC source, it's simply going to add it in there, meaning the reference level is going to shift up or down depending on the value of our DC source. So if you have a DC 5-volt signal and you have a waveform like this, it's going to shift your waveform like that. And the difference in the shift is the DC voltage that we are applying. Okay, the DC voltage is 1 volt. It's going to shift your waveform up by 1 volt. If you apply 2 volts, it's going to shift upwards by 2 volts. If you apply 5 volts, it's going to shift it up by 5 volts. Okay. So this is what we need to accomplish. We have our V in of t, and we are supplying it at the output terminals. The choice of resistors, it's a resistive network, so choice of resistors is arbitrary because we haven't been provided any other information. So if no information is provided, you can make assumptions, or we don't need to make an assumption. Here you see 10 kilo ohms, but instead of 10K, you could choose 1K, you could choose 100K, you could choose 100,000, 1 mega ohm. It wouldn't make any difference because we are not told of any other requirement. We are not told the current, we are not told about power, we are not told about anything else. So we'll just neglect that portion and we just start with like 10K. So V in of t and 10 kilo ohm resistor is going in there. Now we know that we're going to apply 5 volts. And so that gives us the 5 volts DC input. So from the provided network, we are provided a 9-volt DC source, and we need to obtain 5 volts from it. And that's easily done. We use a voltage divider network, use multiple resistors in series, and we can obtain any value we want. If we have 9 resistors, each with equal value, 100 ohms or 1 kilo ohm or 10 kilo ohms, and you connect them all in series, you can have 1, 2, 3, 4, 5, 6, 7, 8, 9 volts, 9 levels of voltage all coming out. Okay, so voltage division is an easy way or easy and quick way to implement that kind of voltage transfer. So we have 9 volts and our desired value is 5 volts right here. So provided source is 9 volts. Desired source is 5 volts. So we have to obtain 5 from 9. And we can implement that using a series resistive network, meaning series connected resistors. Okay. All right. To do that, we can do this. We have our 9-volt source. And we have 2 resistors connected across it. And we're going to take the output across any one of those resistors. Okay. We want to keep both circuits at the same reference level, so we'll take the output across the bottom resistor, not the top one. Okay. We want to keep the reference level the same. So the bottom one is connected to the negative end of the first supply, and the negative end of the other supply, V in of T, will also be at that same level. Otherwise, you will not obtain correct values. Okay, so all 3 points, wherever you see in the circuit, you see this triangle, that means they're all connected together. Okay, so if we call this R1 and R2, this R1 and R2 is feeding into our resistive network. And so let me draw this. And then let's see, this one. That's how the circuit will look. And this is V in, or V in of T, V in of T, and that is our actual V out of T. Okay. We already chose this to be 10 kilo ohms. Now we just need to find the value for R1 and R2. Okay. And the desired output here must be 5 volts. Okay. So we are reverse engineering, so to speak, which is what all engineering or all system design is. You have a goal in front of you, and then you're going to design a system to accomplish that goal, right? 130. Okay. So far, so good. Any questions? Okay. All right. So what do we do? Well, Thevenin and Norton equivalent circuits. We want a desired voltage source. We want 5 volts as our output, right? So that's our Thevenin voltage. 5 volts is our desired Thevenin voltage, and 10 kilo ohms is our desired Thevenin resistance. And that's an application of Thevenin's theorem. Again, 5 volts is our desired Thevenin voltage, and 10 kilo ohms is our desired Thevenin resistance. Desired VTH is 5 volt. Desired RTH is 10 kilo ohms. And this is going to give us both, right? We've seen this circuit before. Two resistors with a power supply. We know the equations. We know the equations that go on this circuit or that describe this circuit. Okay. So RTH is going to be R1 in parallel R2, which is R1, R2 divided by R1 plus R2. We know that we want this to be 10 kilo ohms. Okay. And then from voltage division, VTH is going to be 9-volt source times R1 over R1 plus R2. And this, we want it to be 5 volts. So the ratio of R1 over R1 plus R2 is 5 over 9. Okay, it's 5 over 9. Let's take a pause while you look over the equations, and then let me know if you have any questions. Okay, so the question being asked is, why are we using this as a 10K? 10 kilo ohm. These are arbitrary values. So completely arbitrary. They are an assumption on our part because we haven't been provided any current values or current information. And so we could do this problem by choosing both as 1 kilo ohm. We could choose like 5 kilo ohms. We could choose 100 kilo ohms. It would not really matter for the purposes of this design, because there's no other value provided to us. We simply make an assumption and kind of roll with it. So we could solve this design with either 10K or using 1K or 5K or any value for that matter. Unless we are given, like, say, okay, design this circuit, but ensure that the output current is within, like, I don't know, 100 milliamps or something. And then we have to take those into consideration. Yes. And those resistors are something that will determine. Because we're trying to obtain a combination where we get both 5 volts and then 10 kilo ohms. So this equation gives us, this is from voltage division, that gives us the ratio that we need. And then this gives us the ratio for both the resistors. Okay. So here I can write the ratio of R1 or R1 plus R2 is 5 over 9. Okay. So that's one equation. And the other one, of course, is R1, R2 over R1 plus R2 is 10 kilo ohms. We can combine both of these to obtain this. Okay. Any other questions? Let's take a pause and think over that. Let me know if you have any questions. Yes. Which one? Why does it have more? That was the design requirement. So that's like at the beginning. Yeah. Oh, because we are our output, our desired output is plus 5 volts. Yep. Okay, so I understand the question. So because it's going from -5 to +5, how is it just going and ending up with just +5? Yeah, effectively we are like cutting this out. Like a different kind of design problem would be how to completely shift it up and say 0 to 10. So that's your question, right? Why is it 0 to 5 and why is it not 0 to 10? That's that's just the example. That's just the random example. I'm confused. Oh, how how do we know that we desire this as 5 volts? That's a good question. The question being asked is how would we know? Like there's a design statement, there's a problem statement in the design, but how do we know that we need exactly 5 volts at the output, right? That's what you're asking. That's a good question. So working backwards, let's see. Uh, Working backwards on this one. How can we link this? This is just an example that I had, so from the notes, and so I just automatically did it. I never questioned it. Um, Actually, I don't have a good answer for you right now. Let me think on it, and I'll get back to you. Just remind me next class if I don't already bring it up at the top of the hour. Just remind me again. Okay. All right. Let's see. Okay, so we have this. So we plug that into the other equation, and we can obtain this one, right? And then once we solve for R2, we get R2 as 18K. And then you plug it back into the RTH equation and you calculate R1. Okay. And that's how we can calculate the values for both resistances. All right, let's take a pause. Let me know if you have any questions. Yes. So let's see. You're asking about this circuit? Question being asked is if we add 5 volts to this, wouldn't it automatically shift everything up? It's a good point, but we have resistors here equal in value. And so they will cause a voltage drop across those resistors. So anytime, so this is at a constant 5 volts, right? If this waveform here goes from -5 to +5, if that waveform is also at +5, then the current here at that point is 0. So there is no voltage drop here. When this waveform, V in of t, is at 0 volts, remember V in of t has this shape, right? So it goes to 0 volts, plus 5 volts, goes back down to 0 here, and then goes to minus 5, right? And so anytime this is at plus 5 volts, current through 10K is 0. That means voltage across that upper 10K is 0 volts. If, not if, when this waveform V in of t goes to 0 volts here, and this is plus 5 volts here, what's the current that's flowing through there? 5, not 5 divided by 10K. But voltage across that resistor is plus 5 volts. When it goes to minus 5 volts, voltage across this one would go to 10. And similarly, this resistor right here at the bottom also drops voltage across it. And that's why they're both taken at the same value. If they were not the same value or the different values, then we would obtain 0 to 10 volts. Okay. And we can verify this. We can verify this circuit by running a simulation in SPICE. So you can create this circuit. Okay. Once we create the circuit, we can apply a resistive network. And once you apply a resistive network, by the way, this R1 is just positioned here, but because when we design in LT Spice, we can like cross-link that way, but it's the exact same design or exact same circuit as this, right? And so you create the circuit in LT Spice and you run through the simulation, and you're able to see this is plus 5 volts. This is minus 5 volts, this level right here. So plus 5 volts, minus 5 volts. And then the output, you will see going from 0 to plus 5. The way we would do this in LT Spice is we would assign a voltage source V1. And in the advanced settings, you choose pulse. And in pulse, you specify, have you done this before for the lab? There was one nod and there was one shake. Okay, all right. So start voltage is minus 5. End voltage is plus 5. Okay. Then 1 micro, I forgot what 1 micro. Oh, it goes from 0 to 1 microseconds in steps of 1 microseconds. And then what is the pulse? You simulate this for, was it 1 millisecond? Oh yeah, 1 micro transit time. So you got to describe the circuit, how long it takes for it to transition from minus 5 to plus 5. So you make it a very small value, either 1 mu. So the U stands for micro. Either do 1 micro or do 1 nano. You can do 1 N also. You can do 1 N also, and it'll still work fine. And then 1 millisecond pulse, and then you're simulating from 0 to 2. So this is 2 milliseconds, and each half cycle is 1 milliseconds. And that's what this is describing, the last two numbers at the end. Okay. And then instead of .dc or .op, you're doing a transient analysis. So you choose transient analysis. That would place a .tran on there. You're simulating from 0 to 4 milliseconds and in steps of 0, 1 micro. So you can do this outside of class when you're reviewing this slide, and then you'll be able to see this V out clamped from 0 to plus 5. Okay. So again, as I said, it's the same circuit that we are seeing here. And you can simulate that in LT Spice. Okay. Now that we have 3 resistors in there, if you're simply looking at the output, meaning the 2 output terminals, the 3 resistances will have our EQ. And because you have 2 voltage sources in there, if you short them all out, all 3 resistors will be in parallel. And so the total RTH, or Thevenin resistance, of the entire circuit is those 3 resistors in parallel, which gives us 5 kilo ohm. Which we already knew because we had 10K and 10K in parallel. So 10K and 10K in parallel would give us 5 kilo ohms. And that's the total Thevenin resistance of that circuit. Okay. Let's take a pause. Let me know if you have any questions. Any questions? No. Okay. All right. So hypothetically speaking, let's say you're trying to sell this, not sell this, but you are designing this for a customer. Customer comes back and says, this worked great, but now we want a circuit with a lower current. So lower current means high resistance. So maybe low power application, perhaps, let's say. Like you don't know and you don't really care. Customer is, we want a circuit that has a higher Thevenin resistance. Instead of 5 kilo ohms, we want you to design something with 25 kilo ohms. So what do? Do we redesign everything? Or do we recalculate everything? Not really. The answer is already there because it's a linear circuit made comprised of linear resistors. Well, resistors are linear, meaning the voltage and current has a linear relationship. Voltage hasn't changed. The only thing that is asked to change is the current. So this goes back to the earlier question that was asked. Why are we choosing 10 kilo ohms? Why not something else, right? So here's the answer I was saying. It's because no other information is provided to us, right? It does not say that design this for current output of such and such limitations. So now the customer comes back, says, redesign this for low current power applications. That means high resistance. High resistance, V equals IR. V is not changing. It's still 5 volts. I is changing. So R must change. And because it's a linear relationship, you can scale it up. And so if RTH is 25K, you multiply the resistances by 5 times, and you have your answers. Okay, 18 kilo ohm now goes to 90, 10K goes to 50, and the other one goes to 112.5 kilo ohms. So the resistor values depends on the desired output. On the converse side, if the customer said that we want to use this for high current application, for high current, resistance would be lower. And so you would lower the resistance, or you would scale the resistors down based on your desired output. Does that make sense for everyone? Okay. Expect something similar like this on the quiz and the final exam. Something similar. Okay. Okay, so we have about 10 minutes left. Just want to quickly do this. In basic physics, you may have studied, you've studied resistance. And did you all study conductance at all? Okay. So resistance R is R, and R can be determined from this equation, the rho L over A. Does that ring any bells? Rho L over A. Okay. The rho is the Greek letter rho, R-H-O. It is a material property. It is the resistivity of a material. So if you have a piece of material, doesn't matter what shape, it will have some resistance. A is the cross-sectional area of that material or that piece of material, and L is the length of the material. So resistivity times length over the cross-sectional area gives you the resistance of that piece of material. Whether it's a metal or insulator, does not matter what it is, but that gives you the resistance. Units for resistance are ohms. This is the only quantity I can think of that uses a symbol or a Greek letter for its units, omega. Okay, this is uppercase omega. Uppercase omega is used to note ohms. Okay. Reciprocal of resistance is conductance. Is noted by the letter G. Unit is named after the German physicist Siemens. It's SIE or SEI. Can't remember at this point. Siemens was a German physicist or Austrian, I believe. Let's see. Nope, I have it correct. It's SIEMENS. And just sometimes use SA. When I first learned it, when I was a student, that was 30, 40 years ago. It's also sometimes known as MO, MHO, simply the reverse of ohm. Okay. So why are we talking about this? Is because sometimes circuit analysis, when you're faced with parallel circuits, it is easier to perform calculations if we talk in terms of conductances versus resistances. With resistances, we have to take what reciprocal of the sum of the reciprocals. If you have conductance and you have a parallel circuit, you can directly describe GEQ or REQ simply by taking the sum of these conductances. Meaning you take the reciprocal of the resistances, note it down, and you simply add those values up. And so it helps or makes analysis easier. Obviously, with modern day calculators and computers and tools, it's not as, it's not as, I wouldn't say relevant, but as important. Okay. But let's say you have a circuit with parallel resistors, and we want to find the values for the currents that are going through each one of these branches. So I1 and I2. This, of course, is current division, right? Current division. Well, what we do is first we find voltage due to the parallel combination of I1 and I2. Sorry, R1 and R2. And then we apply Ohm's law again. So V equals total current I times Req. And then each individual current I1 is V over R1, and I2 is V over R2. Well, Req for this parallel combination is this R1 times R2 or R1 plus R2, right? So then what do we have? We plug this equation right here, and then we obtain R2 over R1 plus R2 times I. Okay. Wait. Yeah, R2 over R1 plus R. Let's see. I1 is V over R1, and V is R1, R2 over R1 plus R2. And this is divided by 1 over R1 times I. So R1, R1 cancels out, leaves behind R2 over R1 plus R2. Yeah. So now we can have a similar expression if we take conductances. So I have G1, which is the reciprocal for R1, and we have G2, which is the reciprocal for R2. So 1 over R1 and 1 over R2 gives us G1 and G2. Almost out of time. Okay, so then we can take that same expression, I can modify it, and I can obtain I1 is G1 over G1 plus G2 times I. Okay, because any parallel resistive network is going to split the current, hence it's known as current division. So the technique that we use to directly find these currents is known as the current division principle. And so we can apply current division principle by finding Req. Req, same parallel combination. So it depends on how many parallel resistors we have. If you have 2 or 3, it's easier. But if you have more than, like, I don't know, if you have like tens or hundreds of resistors in parallel and you want to find the current, then it's easier to simply work with conductances. Okay, we simply take the conductances now and then add it up. So we got G1 over G1 plus G2. If those 3, we would do G1 over G1 plus G2 plus G3. 4, then you add up all 4. 5, then you add up all 5. So it makes analysis and calculation far easier and simpler than if it was simply working with resistances. All right, and so that's where we use conductances. Okay. We are out of time. There's still a couple of slides left, actually. We'll talk about current division, voltage division later, but this was the home activity in the previous slides. So please ensure, if you have not done it yet, you have the solution here. Go ahead and do it and see if you can obtain that same solution. This was what we talked about at the end of the previous slides on Friday. Okay, so go through these and then solve it manually if you want to as practice, but definitely do it in SPICE. If you do it in LT SPICE, you should be able to get the verification for those answers. Okay, we'll end class here today and we'll pick up here again on Friday.